1.4 is composition of mixtures. So our outcome is I can explain the quantitative relationship between elemental composition by mass and the composition of substances in a mixture. So we're taking this composition by mass idea and we're going to extend that to then apply to mixtures as well. So chemical analysis is a useful tool to determine the formula of a compound, but also in the composition of a mixture. So we can use the same tools that we were using in the composition of compounds in 3.1, we can also apply that to mixtures. So one useful way to determine the purity of a sample is to compare the percent composition of the elements in the compound to known values. So let's take a look at an example of that. Let's say that I have a bottle of sodium chloride on the shelf and I think it's contaminated. So I do a chemical analysis to determine the percent by mass of chlorine, and I find that it's 55%. So which of these is most likely the contaminant? So first what I need to do is calculate what the percent by mass of chlorine is supposed to be in sodium chloride. So I'm just going to take the molar mass of the chlorine and divide that by the molar mass of sodium chloride. And I get 60.7%. So we see that we've analyzed the sample and found it to be lower than 60%. So we got to figure out which of these three would cause the percent to decrease. So the first choice here is NaI. That's 0% chlorine. So if this is the impurity, it's not going to change the percent by mass of chlorine into a number like 55. So the choices that we have really come down to KCl and LiCl. So when I find the percent by mass of chlorine for both of these, I see that for LiCl, it's 83.6. So if LiCl were the impurity, that would drive up the percent by mass up from 60 to something higher. We saw that the percent by mass of chlorine decreased from 60 to 55. So the impurity must be something that's going to dilute the percentage of chlorine. And that's going to be KCl because that has a lower percent by mass. In the next question, you observed a carbonate decomposition. So this is very similar experimentally to what your lab 1 is going to be. But the difference is this is a pure substance and this is going to be, in our experiment, a mixture. So here's the masses that we found during the video. And for observations, there's a lot of observations that we can have here. And these are important because a lot of times on the AP exam, they'll ask you questions where you have to justify your response with some kind of observation. So few observations here. We know that we produced CO2. There were a couple of tests for that. We saw steam forming. We saw that the Bunsen burner was moved and adjusted to evaporate water. And really important here, this was not heated to constant mass. So let's take a look at some math here. So there's a lot of ways that we can calculate the atom economy. Don't get hung up on the details of the different ways to calculate it. What you need to understand is that atom economy is a measure of how much of my reactants actually ended up becoming the desired product and don't exist as wastes. So in this case, my desired product is sodium carbonate, but I see that I have some waste products here in the form of H2O and CO2. So because all of the reactants didn't become products, the percent by mass here, the percent atom economy is about 63%. So remember, percent yield is like a measure of how well you did the experiment, how much of what you were expecting did you actually get. Whereas atom economy is how efficient is the reaction. The lower the atom economy is, that means that you had more wastes that were produced as waste products. So how is the mass lost related to the starting mass of material? So the mass that was lost was due to the formation of water vapor and carbon dioxide gas. So those escape the test tube. Now, if you know the starting and ending masses of the test tube, you can figure out exactly how much carbon dioxide and water escaped. So now we want to find our percent yield of sodium carbonate. So percent is always the part that you are interested in over the total, over the whole. So I want to know how much did I actually get versus what I was expecting to get. So based on the math in the video, we come up with 3.52 grams of sodium carbonate. And in this case, we see that the percent yield is going to be 100% because her actual yield is the same as her theoretical yield. This is probably due to the fact that she had really good technique. All of the sodium hydrogen carbonate stayed in the test tube. There wasn't a lot of transfer and places where mass could be lost. But we also can't be too confident in this value because she didn't heat it to constant mass. So there could be some unreacted sodium hydrogen carbonate that is contributing to that 3.52 grams of solid that are left behind in the test tube. So what is another possible consideration from principles of green chemistry that we can use to compare the efficiency or greenness of reactions? So atom economy measures how much of the reactants end up in the desired product. So from lab 1, that is the create no waste principle. We could also compare the energy input for two reactions or the toxicity of materials for two reactions. We really want to use these different efficiencies to pick between two reactions. If I have two ways to do something, which way is going to be more efficient and more green? So our reflection questions here compare pure substances and mixtures in terms of composition. So pure substances contain only one type of molecule or one type of formula unit, whereas a mixture is going to be different molecules or formula units. So pure H2O is a pure substance. Salt water is a mixture of NaCl and H2O. How can percent composition be used as a measure of purity in the sample, and why might chemists want to know that? So we saw that in question 1 here, we know that pure NaCl should be 60.7%, but my sample was less than that. So I can use that as a measure of how pure it is. Now, why does that matter? Well, let's say that I'm doing a reaction where I need 5 grams of NaCl. If I go and measure that out, what I think is 5 grams of NaCl isn't really 5 grams of NaCl. In this case, because the percent is lower, I actually have less sodium and chloride than I think I do. And that really matters if I'm trying to make the chloride my limiting reactant. So it might be that I want to make sure that it all gets used up, something like that. So I'll end up with less product than I'm expecting because I didn't have the amount of starting material that I thought I did. So chemists need to know that. If a sample isn't pure, they need to know that so that their calculations can be adjusted to account for that.